Hi, this is Dr. Xu, teaching design of experiments for engineering research. In this video, I will talk about the randomized paired comparison design. Suppose a hardness testing machine that presses a rod with a pointed tip here into a metal specimen with a known force. By measuring the depth of the depression caused by the tip, the hardness of the specimen is determined. Two different tips are available for this machine, the blue one and the red one. It is suspected that one tip produces different average hardness reading than the other. To design the experiment, we can select one piece of metal specimen and cut it into 20 pieces, and randomly assign 10 pieces to each point tip. This is the completely randomized design we have learned before, but there is one issue with this method. We have only used one type of metal specimen with a specific material and strength characteristics. The finding on whether the two tips produce different average hardness readings will be only valid for this one type of material. But we want to find a more general conclusion that applies to a broad range of different test metal specimens. To overcome this drawback, we select 10 different metal specimens to be tested, so from 1 to 10, and divide each specimen into two parts, then randomly assign one half to one tip and the other half to the other tip. This can be done by simply flipping a coin. For example, for specimen A, if flipping a coin and land with head up, I will assign it to the blue tip. Otherwise, it will be assigned to the red tip. After 1A is assigned, 1B will be assigned to the remaining tip. This process can repeat for the rest of the specimens, and the test sequence for the 20 specimens will also need to be randomized. After completing the experiments, we calculate the result difference for each specimen. Here, 7 minus 6 equals to 1, 3 minus 3 equals to 0, and 3 minus 5 equals to negative 2. Make sure always follow the same sequence when calculating this difference di. This is called the randomized pair comparison design because the treatment combinations are only randomized within a pair. In this example, it is a specimen cut into half and randomly tested the strength using tip 1 for one half and tip 2 for the other half. This is also a special case of randomized block design, which we will talk about in other videos. In this example, the metal specimens are the blocks. Based on the central limit theorem, the distribution of di is a t-distribution with a degree of freedom of 10 minus 1 equals to 9. Although 20 observations have been taken, because these are paired or blocked data, only 10 minus 1 degree of freedom are available for the t-statistic. We can perform a hypothesis testing using p-value. So the null hypothesis is the reading difference true population mean is 0. And the alternative hypothesis is that it does not equal to 0. We select the significance level of 0.05. We will need to calculate the t-value to find the p-value. Just to have a quick review of the t calculation equation, it equals to the sample average calculated from the 10 values minus the null hypothesis value, which is 0 here, divided by the sample average standard deviation. The sample average standard deviation can be calculated by using the population standard deviation divided by the square root of the sample size, which is 10 here. We use sample standard deviation as a good estimate of the population standard deviation, which is calculated using this equation. So in this example, y bar equals to d bar equals to
1 plus 0 minus 2 plus 1 plus 0 plus 1 minus 2 plus 0 plus 1 minus 1 divided by 10 equal to negative 0.1.
s equal to
Square root of 1 minus negative 0.1 square plus 0 minus negative 0.1 square plus negative 2 minus negative 0.1 square, and all the way to the last value, which is negative 1 minus negative 0.1 square divided by 10 minus 1.
If we do the calculation, it equals to 1.197. Therefore, this equals to
1.197 divided by square root of 10 equals to 0.3786.
Therefore, t equals to negative
0.1 minus 0 divided by 0.3786 equals to negative 0.264.
We can find the p-value using the function in Excel. In Excel, I have put the difference values here. And the sample average is calculated by using this equal to average function. So equal to average, I select the values here. Sample standard deviation is calculated by using equal to stdev.s. This .s means calculating sample standard deviation instead of population standard deviation. And also, I select this 10 data set. It returns the sample standard deviation. The sample average standard deviation equals to sample standard deviation divided by square root of 10. So here, it equals to this value divided by square root of 10. And the t-value equals to sample average minus 0 divided by the sample average standard deviation. So the same as what we have manually calculated, the t-value is negative 0.2641. And the p-value is calculated using this function equals to t.dist.2t. This 2t means we are doing a two-tail hypothesis testing, because the alternative hypothesis is the mean not equal to 0. This is the two-sided hypothesis testing. So the first variable is the t-value. Here I used the absolute value of this t because this function only takes the positive value of t. The second parameter is the degree of freedom. In this example, we have 10 values and the degree of freedom is 9. So the p-value is 0.797. We can also use the built-in data analysis function in Excel by using the original data. So the original testing data for tip 1 and tip 2 are here. We need to go to data, and here you should have a data analysis tool. It's not here on my computer, but I can install it pretty quickly by going to File, Option, Add-ins. Here, make sure you select Excel Add-ins and Go, and select Analysis Tool Pack, and OK. Now we have a data analysis tool, and we can select it. Go down. Here we have a t-test paired to sample for means. Select it. OK. Variable 1, select this tip 1. Variable 2, select tip 2 data. And hypothesized mean difference is 0. Significance level alpha is 0.05. The result will be generated in a new worksheet. Click OK. OK. The result is summarized here. What we have is the variable 1, the tip 1 mean, tip 2 mean. The variance, they are quite close. Observation 10 and 10. Degree of freedom is 9, and the t-value is negative 0.26. And we are doing a two-tailed hypothesis testing. So we look at the p-value for two-tail. The value is 0.797, the same as what we have calculated here, this value. So since the p-value is 0.798 and it is larger than the significance level we have predetermined 0.05, we cannot reject the null hypothesis, and there is no significant evidence showing one tip produces different mean hardness readings than the other. Let's look at another example. The shoe soles were made of two different materials, a standard material A and a cheaper material B. The manufacturer wants to know if the amount of wear of the cheaper material is more than that of the standard material A. If not, the company can go ahead and use material B to reduce cost but maintain the same shoe quality. To use a randomized pair comparison design, we randomly select 10 boys, and for the shoes each boy wears, one shoe is made by material A and the other with B. The decision as to whether the left or right shoe was made with A or B was determined randomly, such as by using the flip of a coin. The different colors of the materials is only for illustration purpose, and in practice it will be the same appearance, and the boys do not know the shoes are made from different materials. This is called a blinded experiment. There are several advantages of this design. You may ask, why not only use one boy and repeat the test for 10 times? If this was done, conclusions might apply only to that particular boy. By introducing 10 different boys, conclusions drawn now depends much less on the choice of boys. This idea is a particular case of experimenting to produce robust products. You might say that the conclusions are robust to the choice of boys. Okay, now I see the importance of using 10 different boys, but what's wrong with the design here? I have 10 random boys, and each of them are randomly assigned a pair of shoes made of the same material. This design has the drawback that some boys wear their shoes. More than others. Maybe they work more on rough surfaces. If you assign the same material shoes to the same boy, and the shoes on one boy wear substantially more than other boys, this variation will impact the conclusion. Our design here uses the two shoes with different materials always subject to the same treatment, and we compare the wear B minus A for the 10 boys, and the boys-to-boy variation could be eliminated. The experiment results are displayed in this table, and the number here is the amount of wear with left or right shoe labeled. And the difference is B minus A. This value is always calculating B minus A. We now construct the hypothesis testing. The null hypothesis is the true mean of the wear difference between material B and A equals to 0, so there is no difference. The alternative hypothesis is that the true mean of the wear difference between material B and A is larger than 0, meaning material B wears more than that of A. Also, we determine the significance level of 0.05. We will use Excel to compute the p-value. So the result data is here. We use data analysis. We use t-test paired two-sample for means. Okay. And variable 1 we select for material A. Variable 2 we select material B. Hypothesized mean difference is 0 and the significance level is 0.05. Click OK. The result is summarized in this table. We use this one-tailed p-value because the problem is a one-sided hypothesis, and the p-value is quite small, 0.004. Because the p-value is very small than our significance level, that means if the true mean of the difference equals to 0, the chance of getting a data set like this is very, very low. Therefore, we reject the null hypothesis, and there is significant evidence showing material B wears more than that of A. So material B has lower quality than material A. If the manufacturer chooses material B, the quality of the shoes will be reduced. It is very important to understand that in the randomized paired comparison problem, we are testing if the difference between the pairs are 0, not the difference of the average of sample A and B. So it's not the average of this whole set minus the average of this whole set. If we look at this plot, if we plot the data all together here, the black dot is for material A and white is that for B. And if we consider only the overall dot plot here, the black dots and white dots overlap extensively, and there is no clear indication that one material is better than the other. If you calculate the p-value using the simple comparative experiment data analysis method, the calculated p-value is larger than 0.05, and we cannot reject the null hypothesis indicating evidence support material A and B are the same. But our tests were run in pairs. If we look at each pair of the data here, we can observe that most of the times material B wears more. Here, 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 and here. This is why we use the paired comparison design and use the paired two-sample t-test for means. Okay, this is Dr. Xu. Thank you very much for watching. I will see you in the next video.